Here's lesson 2 of the trigonometry unit. In this lesson, I'm going to teach you about SOHCAHTOA. And by the end of the lesson, you'll learn about how that acronym relates to the 3 primary trig ratios: sine, cosine, and tangent. So let's start with a quick definition about trigonometry. Trigonometry is the branch of mathematics that deals with the relationships between the sides and the angles of triangles, and the calculations based on them. In lesson 1 of this trigonometry unit, you learned about similar triangles, and now we can build on those properties to learn about the 3 primary trig ratios. In this investigation in part 1, we'll specifically learn about the tangent ratio. Notice on the right here we have 4 nested triangles. Let me outline them for you so you understand what's happening. We have triangle ABC, triangle ADE, triangle AFG, and triangle AHI. In part A of this investigation, it asks us if these triangles are similar. Well, remember in lesson 1, we learned that similar triangles are triangles that have the exact same shape, but are not necessarily the same size. And if these triangles do have the same shape, if they are similar, we know all of their corresponding angles would be equal to each other, and their corresponding sides would all be proportional to each other. So looking at these 4 triangles, I think the easiest way to see if they're similar or not is to see if they all have the exact same 3 angles within the triangles. Well, I can see right away that they all have a 90-degree angle in each of the triangles, so that's one angle they all have in common. And also, vertex A was in all 4 of the triangles, so they all share this angle A. That proves that there are 2 angles that are the same in all 4 of the triangles, and that's enough to prove that all 3 of the angles in all 4 triangles are equal to each other. Since the sum of the angles in any triangle is 180, if 2 of the angles in all of the triangles are the same, the third one, this one up top in all the triangles, would also have to be the same in all of those triangles. And I can see based on a parallel line theorem, these are all perfectly vertical lines, so they're all parallel to each other. They're all cut by this line here, so based on the F pattern, or the corresponding angle theorem, I know all of those angles would have to be equal. So we can summarize this by stating how we know that these 4 triangles are in fact similar. To answer part A, which asks if the triangles are similar, I'll say yes. This can be shown through angle-angle similarity. All 4 triangles share angle A, and they all have a 90-degree angle. And then part B of this question asks, which angle do all 4 triangles share? Well, I already mentioned that in part A, they all share angle A. So what I'm going to actually do is I'm going to highlight this angle A in yellow because we're going to use that angle a lot in part C of this question. Part C says, from that shared angle, so from this angle A, find the ratio of the side opposite to that angle to the side that is adjacent to that angle in all 4 of the triangles. So let's start with triangle ABC. So if I zoom in on this here, let me outline triangle ABC. And the question asks us to find the ratio of the side opposite from angle A to the side that's adjacent to angle A. Let's start by figuring out what side is opposite, what side is adjacent. Well, if here's angle A, the side opposite from angle A is the one across the triangle from angle A. And the side adjacent to angle A is the side that's touching angle A, but not the hypotenuse. Notice there are 2 sides that are touching angle A. But side AB, that's the hypotenuse. I know that because it's across from the right angle, which leaves side AC to be the adjacent side. If I count the length of the side opposite from A, it's 1, 2, 3 units long. And if I count the length of the adjacent side, it's 1, 2, 3, 4 units long. So the ratio of opposite to adjacent in that triangle ABC would be 3/4. And now what we're going to do is just repeat that same process of doing the opposite side divided by the adjacent side for the next 3 triangles that we have in our diagram up there. So let's do triangle ADE next. So I'll zoom in on this diagram, and I'll outline triangle ADE. From angle A, the opposite side is going to be the one across the triangle. It's going to be side DE. And the adjacent side is the one touching angle A, but not the hypotenuse, which would leave this side right here, AE, as the adjacent side. And if I were to count the length of the opposite side, it's 6 units long, and counting the length of the adjacent side, it's 8 units long, which means the ratio of the side opposite over adjacent in triangle ADE is going to be 6/8. And notice 6/8 reduces. 2 goes into 6 and 8, 3 and 4 times respectively, so it reduces to 3 over 4, which shows us that the ratio we got in our second triangle is equivalent to the ratio we got from the first triangle. And that's because these triangles are similar to each other, so the proportions of the sides are going to remain constant. So when we do this for the next two bigger triangles, we should get ratios equivalent to 3 over 4 again. Let's do them really quickly just to find that out. Zooming in, we'll do the next two triangles all at once here. In triangle AFG, opposite side is side FG, and the side adjacent to angle A is the one touching angle A that's not the hypotenuse, which is this side here. And if you counted the length of the opposite side, you would get 9, and the length of the adjacent side is 12. So the ratio for triangle AFG is 9 over 12, which reduces to 3 over 4 again. And then in the biggest triangle, the side opposite from angle A is 12 units long, and the side adjacent to angle A is 16 units long. And 12 over 16, that ratio reduces to 3 over 4 as well. So all four of the ratios of opposite over adjacent in these four triangles are all equal to 3 over 4. And now let's summarize our findings down here below so you can understand what we did here. What we actually just found is called the tangent ratio from angle A. The word or function tangent just means the ratio of the opposite side to the adjacent side from some reference angle. Notice the ratio was equivalent for each of those triangles, and that's because all four of those triangles were all similar to each other. If you have any two right triangles with an equivalent reference angle, they have to be similar to each other based on angle-angle similarity, and therefore they must have equivalent ratios of pairs of sides. And your calculator is actually able to calculate those ratios of sides for any reference angle that you choose. For example, on your calculator, if you type tan 45 degrees, your calculator is going to tell you that that's equal to 1. Because what you're asking your calculator for, you're asking your calculator for the ratio of the opposite side to the adjacent side from a right angle triangle that has a 45 degree reference angle. Your calculator doesn't know what size triangle you have, but it knows all right angle triangles with that same 45 degree reference angle are all going to be similar and therefore have the same ratio of sides. That's why your calculator knows the ratio is 1 without knowing what size triangle you have. And I've drawn two different size triangles here. Notice they both have this 90 degree angle, and they also both have this 45 degree reference angle. Because they have two angles that are equal to each other, I know that all three angles must be equal to each other in those two triangles, making the triangles the same shape even though they're different sizes, meaning that they are similar to each other, which means their side lengths are proportional to each other. And that will all guarantee that if you were to find the ratio of the opposite side to the adjacent side from this 45 degree reference angle in either of those triangles, you'll get the exact same ratio. 1 divided by 1 is equivalent to 3 divided by 3. And also, it might be worth pointing out that we probably wouldn't need our calculator to know that tan 45 should be 1. If we have a right angle triangle with a reference angle of 45, I know that the other angle has to be 45 degrees as well, so that the angles all add up to 180 degrees. And then I can tell that because these two angles are equal to each other, I have an isosceles triangle, meaning that these two side lengths have to be equal to each other. So it doesn't matter what size I make this triangle, make it bigger or smaller, as long as I keep the angles the same, that's going to guarantee it's still an isosceles triangle, so the opposite and adjacent are still going to be equal to each other, meaning the ratio is still going to be 1. As we go through some more examples, hopefully this will all sink in and you'll understand the connection between SOHCAHTOA and similar triangles. So let's go ahead and do example 1, where it just asks us to calculate the tan ratio to the nearest thousandth, so to 3 decimal places, for each of these angles. So for part A, let's just calculate tan of 40 degrees. If you use your calculator to evaluate tan of 40 degrees, first of all, make sure your calculator is in degree mode. And then when you type tan of 40 degrees, you're telling your calculator that you have a right angle triangle with a 40 degree reference angle. And what you want your calculator to tell you when you use tan, you're asking it to tell you what the ratio of the opposite side to the adjacent side is. So in this right triangle that I made up here, opposite from the 40 degree angle is over here, and the adjacent side is the side touching the 40 degree angle but not the hypotenuse, so right here. So when you type tan of 40 degrees and your calculator tells you that it's about 0.839, that's the ratio of the opposite side to the adjacent side in any right triangle that has a reference angle of 40. I don't actually know what the length of the opposite or the adjacent are, but I know their ratio is going to be 0.839, because for any right triangle with that same 40-degree reference angle, it wouldn't matter how big or small I made that triangle, they would all be similar and therefore have the same ratio of sides. And then just test out your calculator for those remaining 3 examples and make sure you can use it to get the correct opposite over adjacent ratios for each of those reference angles in right triangles. So let's do tan of all 3 of them. If you do tan of 55, you'll get about 1.428. Tan of 73 is about 3.271. And tan of 89 is about 57.290. So hopefully now that you understand that each of these tan ratios is just the ratio of the opposite side to the adjacent side in right triangles that have these reference angles, let's move on to learn the full acronym SOHCAHTOA and extend this to all 3 primary trig ratios, not just tangent. Right? The tangent ratio is just one of the 3 possible ratios of sides you can make from a triangle. The other 2 ratios have names as well. If we look at this right triangle here, if this is our reference angle down here, which I have labeled with the Greek letter theta, from that reference angle theta, we know there's the opposite side of the right triangle. We know there's the adjacent side of the right triangle, which is touching the reference angle but not the hypotenuse. And then also, we haven't talked about this yet, the hypotenuse, which is the longest side always across from the right angle. In a triangle, because there's 3 sides, there's different pairs we can match up with each other to make different ratios. We can match up opposite and adjacent to get the tangent ratio, right? I have that written here. Tan of theta equals the opposite side divided by the adjacent side. But we can also make a ratio from the opposite and the hypotenuse. We call that the sine ratio. So sine of theta is the opposite side divided by the hypotenuse. And we can also find the ratio of the adjacent side to the hypotenuse. That's called the cosine ratio. So cosine of theta equals the adjacent side divided by the hypotenuse. Those are the 3 primary trig ratios. And this little paragraph that we have written right here is very fundamental to your understanding of what these primary trig ratios are and how they work. It says if we know a right angle triangle has a reference angle of theta, all other right angle triangles with that same reference angle of theta are similar, which means they're the exact same shape and therefore have equivalent ratios of corresponding sides. The 3 primary trig ratios are shown in this diagram to the right. And let me give you a demonstration in GeoGebra, which will hopefully drive this point home to you. Notice I have this right angle triangle here with a reference angle of 30 degrees. I've got all the side lengths labeled, and off to the right here, I have it calculating for me the ratios of opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. Those are the sine, cosine, and tangent ratios from the 30-degree reference angle. Now here's the important thing. If I were to make this triangle bigger or smaller without changing its reference angle, so if I keep the angles in this triangle the same but make the triangle bigger or smaller, that's going to keep the triangle similar to this one, and these ratios that I have being calculated on the right, it's going to make them stay the same even though the side lengths are going to change. So watch, as I make this triangle bigger, the triangle is still similar because the angles are still the same, so the ratios are staying equal even though the side lengths are changing. Now, of course, if I change that reference angle, the triangle is no longer similar, and therefore the ratios are going to change. So notice as I change the angle, okay, now the ratios are changing. But if I keep the angles the same, but change the size of the triangle, the ratios all stay the same. So if you typed sine of 37 degrees on your calculator, it would tell you that the sine ratio is 0.6. So hopefully that demonstration helped. And also I should point out this acronym SOHCAHTOA that I've been talking about, you can see it written right here, SOHCAHTOA. That's just a way of remembering which of these 3 primary trig ratios corresponds to which ratio of sides. Notice, SO means sine of a reference angle equals opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So if you can remember this saying, SOHCAHTOA, You'll remember which ratio of sides corresponds to each of the primary trig ratios, sine, cosine, and tangent. And now let's move on to the next example, where we're going to just practice labeling opposite, adjacent, and hypotenuse in a right angle triangle. So in this right triangle, here's my 90-degree angle, and here's my reference angle, angle theta. It says, from that reference angle of angle theta, label the adjacent, opposite, and hypotenuse. Well, hypotenuse is always across from the right angle. It's the longest side. The opposite side from the reference angle is the side across from angle theta, and the adjacent side is the side touching angle theta that's not the hypotenuse. And now let's move on to example 3, where it says state the sine, cosine, and tangent ratios for angle theta. There's our reference angle. So I'm actually going to write the acronym SOHCAHTOA off to the side here, because that's going to help you remember which primary trig ratios, sine, cosine, and tangent, relate to which ratio of sides within the triangle. So in this triangle, I should start by labeling opposite, adjacent, and hypotenuse. Hypotenuse is probably the easiest. That's always across from the right angle. The opposite side is the side opposite from our reference angle. Let me actually highlight that reference angle. And the side opposite from angle theta is the one across the triangle from it. And the adjacent side is the side touching our reference angle, angle theta, but not the hypotenuse. And what we want to do is write the sine, cosine, and tangent ratios for this angle theta. If I want the sine ratio of angle theta, based on SOHCAHTOA, I know that's the ratio of the opposite side to the hypotenuse, which would be 5 divided by 13. So sine of theta, I can say is the ratio 5 over 13. If I want cosine of theta, based on SOHCAHTOA, I know cosine of the reference angle equals the adjacent side, 12, divided by the hypotenuse, 13. So cosine of theta is 12 over 13. And then tan of theta, based on SOHCAHTOA, it tells me that tangent of the reference angle equals the opposite side over the adjacent side, which would be 5 over 12. And now we'll learn later in this unit how we can then use those ratios to solve for angle theta. We'll actually be able to figure out what angle theta is. But for now, I just want you to practice being able to write the ratios from a given reference angle in a right triangle. And then the last example is really just to make sure you can find these functions on your calculator. Example 4 says calculate each of the following. In part A, we just want the sine ratio of a 30-degree reference angle. If you use your calculator, if you type sine of 30 degrees, it'll tell you it's equal to 0.5 or a half. And as a reminder, what does this mean? It means if you have a right angle triangle with a reference angle of 30 degrees, the ratio of the side opposite from the 30 degrees, so this side here, to the hypotenuse would be 1 over 2. Now, it doesn't tell us for sure that these side lengths are 1 and 2 respectively. It could be 2 and 4, 3 and 6, or any two side lengths that have a ratio of 1 over 2. And we're able to know what the ratio would be because if I were to make this triangle bigger or smaller without changing the reference angle, all the triangles are similar, meaning that their side lengths all have equivalent ratios. And this triangle I drew here is actually a special triangle. You'll learn more about that as you progress through trigonometry. If on your calculator you type cosine of 60 degrees, you should also get 0.5 or a half. And if you type tan of 10 degrees, you should get about 0.18. So that's the end of this intro lesson to SOHCAHTOA. Hopefully after this very intro lesson to this concept, you're able to look at an answer like this and understanding that what it's saying is, in a right triangle, from a reference angle of 60 degrees, the ratio of the adjacent side to the hypotenuse is 1 over 2, right? Cosine is adjacent over hypotenuse. It's not the actual side lengths, it's just the ratio of sides. So go to Jensen Math, make sure you try out the practice questions from the free resources I have there, and then continue watching through the rest of this unit so you can become an expert on trigonometry.
Jensen